Let's talk about some root locus examples. So again, root locus is going to be a kind of graph of the migration paths of the poles of the open loop system equation, transfer function that is, towards zeros. The zeros can be real zeros or they can be virtual zeros, which we kind of envision to be out here at a radius of infinity. Let's talk about some formulas that are going to help us kind of discover the picture here, and then we'll do a lot of examples. Okay, so if you remember, when we talked about this before, the migration paths are what we're going to be trying to depict here. We had a few rules that we went over, and the starting rule, stopping rule, and real axis rules are going to be really useful, and then we'll also do some examples with the collision rule. So rules 1 through 4 are really helpful. Okay, so symbolically, the number of zeros is going to be m. We'll just call that m. The number of poles, as you probably guessed, will be n. And then to discover the number of virtual zeros, we'll call that q, lowercase q, and we'll let that equal to n minus m. Okay, so if there is not a real zero for a pole to migrate towards, it will migrate towards one of these virtual zeros. There's a few formulas that are going to help us kind of discover the way things look. One is the angle of the asymptotes, and so that'll be a psi sub a and that'll be, of course, with respect to the real axis. So this equation will be 2k plus 1 over the q, and that'll be multiplied by 180 degrees. Okay, so k is actually going to be an integer index, and so you start at 0 and you increase it as you need to. So you'll come up with multiple values for the asymptotes depending on how many you have. Okay, there is another formula called the breakaway points. I'm going to put points because there could be multiple. And then these are also called the breakout or break-in. Okay, whereas an asymptote would have a migration path that is, say like a pole is moving towards a 0, it'll have some kind of a curvature to it. The breakaway points, those are points where, say you've got two poles and we're using the collision rule. We have two poles that are moving towards each other and they break off and they collide. For our rule number 4, we knew that was 90 degrees, but in every other case, we want to find out what that actual point is. Maybe we know the degrees is 90, but we want to find out what point that is on the real axis, and we'll be using this in some of our examples. In general, when I think about this as the GOL, aside from the K, we'll have some numerator over a denominator. And the reason I'm not using the P and the Q is because I don't want to have this K be a part of it. But the numerator and the denominator here. And so our formula is actually just the formula for finding the maximum or the minimum. And we can write it just like this. Take the derivative of the denominator, multiply it by the numerator, and subtract off the derivative of the numerator times the denominator. And we will use this quite a bit in our examples as we go through. So we have this formula. We have this formula with the angles of the asymptotes right here. And then we have another formula called the angle of arrival and departure. And there are a lot of calculations that you can do to completely describe the way this picture looks. Where I feel is necessary to draw the line is here. I want to make you aware of this formula, but it's not necessary, I think, that we go this far. And there will be things as we go through the examples that I'll mention. Well, you could take it a step further, calculate this, calculate that. But, and there we go. And there are lots of formulas in your book that describe, and all of these, maybe not in the exact sense. Maybe they don't put Q here in your text, and maybe they don't call this capital N, capital D. But these formulas in one form or another are in your text, and that'll be in chapter 7 if you have version 13. Okay, so we've covered the formulas, the main formulas that we'll use. Let's go ahead and do some examples. Okay, so as we walk through this, the thing that we will need is, let's say this is example number 1. We'll first need to start out with an open loop transfer function for our system. Okay, remember we're using the open loop transfer function, and we are revealing the behavior of the closed loop transfer function as the k parameter is varied, usually starting at 0 and going to some maximum, which is close to positive infinity for our purposes. Okay, so our first example, let's just start with an s minus 4 on the bottom here. Okay, so let's write down everything we know about this system, and we'll get our axes ready. So we'll be plotting on the complex plane here. Okay, so I know that I have how many poles and how many zeros. Well, poles and zeros. Okay, so the number of poles is actually 1. We know that the pole is at positive 4. And how did I know that? Just from looking at it, yeah, I could tell that positive 4 would solve this equation and make it 0. But what you can do is kind of envision taking this denominator, setting it equal to 0, and then solving it. And that's really how you get the value. Okay, and so positive 4. And then we have 1, 0. And that 0 is actually at 0. Okay, so let's see, do we have any virtual zeros? And the answer is no, these are equal. Okay, so let's go ahead and plot this. This should be a simple one. All right, so a 0 is a circle or a 0. That'll be at 0 for us. And the pole is an x, and that'll be at positive 4. Okay. All right, so we're not quite done yet. If we have anything on the real axis, another good thing to do is to use that real axis rule where we are moving, like perhaps moving our pin across here, and then looking rightward and counting the number of zeros plus poles that we've already marked. So I have 0, and that's noted as positive, 0, 0, 0, and then I have 1. 1 is an odd number. Once I get past here, I have that 1 pole. So I can mark the migration path until that number turns even. So at this point, I have the 0, so this plus this, I have 2 even, so no more migration path past that point. Okay, so now one more thing I can do is I know the direction of the migration, because we know that poles will migrate towards zeros always. So we can draw an arrow like that. And this, once we, of course, label where everything is, make sure you do that. I almost forgot. We have a completed locus. So that is the completed locus. Okay. All right, so let's do another example. That one's pretty simple, and we'll do a couple of really simple ones. So let's say that we have an open loop transfer function, GOL of S, and let's have S minus 2 on top, S plus 3 on bottom, and then we'll also have an S minus 4 on the bottom as well. Okay, so let's fill out what we know so far about this problem. We know that we have number of poles should be 2, because I have 2 poles down here on the denominator. For the zeros, I have 1 0, and then therefore I should have 1 virtual 0. Okay, so we should expect that we're going to have a migration towards an infinity point somewhere out there in this particular locus. We'll go ahead and get our plot prepared. Okay, and where are our poles? So if we look at our denominator and we think about setting this equal to 0, what solves that? And the poles are at -3 and +4. The 0, there's only 1, is at +2. Okay, so let's go ahead and mark this. We have a 2, and there's our 0. We marked it with the circle. Our poles at -3, and then also at +4. Okay, let's see. We got all of these marked on here, so there were 3 items to mark. Okay. So let's go ahead and use our real axis rule to fill the real axis migration paths. Remember, whenever you have something on the real axis, you'll want to use this, and that occurs quite often. So moving the pin across here, 0, 0, 0, 1, that's odd. I can start filling things in until I get to the even number after that 0, and nothing until I get here. And now we have 3 total pole plus 0. It's an odd number, so move this across here and just mark that migration path. Now once we get out here, nothing else is going to happen of interest out here, so I'm going to make this symbol kind of like a exaggerated resistor kind of symbol, and that just kind of symbolizes that there's really nothing else of interest happening that we don't already see happening here. And this goes out to -infinity. All right, we can actually fill in the directions now, because we can see that this pole is moving to this 0. Poles always move towards zeros. And then for this one, remember we have this virtual 0 at radius infinity out here. And so this pole is migrating out to that -infinity along the axis. And then this is now our completed locus. And you may be wondering, well, okay, we used the Q formula, that's pretty simple, but we haven't used, say, our breakaway points or anything like that. So we will use the breakaway points momentarily. We're going to do a lot of examples, but if you want to, you can always go ahead and calculate that, and it will either make sense or not make sense per your locus. And you'll look at the points you come up with and evaluate, does that happen within a migration path? And the answer in this case, if we did calculate that, would be no, that we would not get an answer that would fall within the migration path. So we would know that we don't even need that point. So to do the calculation of the breakaway point, well, you do it if you don't know, and then it gets revealed as you evaluate against the locus that you already have. Okay, let's do another example. Okay, so for this example, let's have a GOL of S that has, let's say, a 1 on top, and then we'll have an S plus 3 and an S minus 4. Okay, so for the number of poles, you can see that we have 2 poles for this problem. For the number of zeros, how many zeros do we have? We actually have 0. There are no S's at all up here. There's nothing that we can do to make this this numerator equal to 0. There's no S that we can choose to have that happen. It's always equal to 1. It's actually 0. Okay. All right, so then we know if we calculate Q, we should get 2 virtual zeros. Okay, so where are our poles? So let's examine the denominator. Our poles should be at -3 and +4. Okay, and again, we don't have zeros for this plot. Let's prepare our axes. Okay, and so let's go ahead and mark our poles on here. So we have a +4, mark that right there, and then we also have a -3, and mark that one. Okay, since we have two markings on the real axis, let's use our real axis rule. And so we have nothing, it's even, and then it's odd if we look rightward. We have 1 pole, so that's an odd number. We have 1 of something. So mark that until it becomes even, which after this pole, we now have 2, so that's an even number. No more migration path that we need to mark. Okay, so what happens here? We're not done, of course, but where do we go from here? Well, if we look back at our rule list, rule number 4 was the collision rule. And so that actually said if we have 2 poles that are migrating towards each other along the real axis, at some point they will deflect off at plus and minus 90-degree angles. That's what's going to happen here. That's an example of that. So at some point, these will deflect off. How do I know that point? That is a breakaway point. So we need to use the breakaway point formula. Okay, let's get that written out here. So the breakaway point formula is in D. If we say that this is N and this is D, the denominator, we can complete that here and set that equal to 0. And again, we're just finding the maximum and minimum. Okay, so if we fill this out, we have N equals 1, D equals the S plus 3 times S minus 4, which turns out to be S squared minus S minus 12. If we take the derivative of the denominator or the numerator, that's going to be 0. And the derivative of the denominator then, if we look at that, should be 2s minus 1. Let's plug this into our formula, and we get that 2s minus 1 equals 0. In other words, the point that solves this is positive 1/2. Okay, And so we have one solution here. That means that we have one breakaway point at 1/2. So if we have one, it occurs here at positive 1/2. So is that within our migration path? Yes, it is. That makes sense for our locus. So they deflect off at positive and -1 infinity. At this point, 1/2. Mark that 1/2 right there. Okay. How do I know that they're going to positive and minus infinity? Those are actually where our virtual zeros are. So we have two virtual zeros. So this is how I know that we're going to reach those extremities. Okay, so this is now our completed locus. And that's what it looks like. Okay. All right, so let's do another example. All right, so for example 4, let's have a GOL of S equal to K times S over S minus 4 squared, just like that. Okay, prepare our plot here. Okay, so let's fill out what we know. N equals 2, because we can see we have two poles here. And M, our number of zeros, the numerator, is equal to 1. I can see that I have one solution here to make this equal to 0. Okay, so Q then should equal N minus M, which is 1. So we have one virtual zero. Okay, so where are our poles and zeros? So we have a 0 at 0, and we have poles at, let's go ahead and set this denominator equal to 0, S minus 4 squared equals 0. That means that S equals then 4, positive 4, and it has a multiplicity of 2 actually, so it's repeated. So we have two poles that occur at the positive 4. Let's go ahead and mark that. And if you have two poles that occur at the same point, just kind of make an X that looks like this, where you can tell that there's two markings, but they're on the same place. Okay, and the 0 is at 0. Okay, so let's use our real axis rule, because we have zeros and poles that are on the real axis. Okay, so I move my pen across here, and it's even, and it's still even. And then until we finally get past this 0, that's when it becomes odd. So we fill in all of this. Let's make our special marking out here. Negative infinity goes all the way out there. Okay, so you may think, well, okay, I can tell that there's a migration path here, but these two poles are on the same point. How can they possibly migrate? Well, as you do more and more examples, you'll see that these two poles being on the same point, that they're actually counted as colliding. They're on the real axis and the colliding. So you can use the collision rule, rule number 4, and say that they deflect off. So do they go to positive and minus infinity? Well, they kind of start out that way. We know that we have a 0 here. We know that poles go to the zeros, but we have no migration path here on the real axis. So what's actually going to happen, the only thing that can happen, since we have this path here, is to have the poles come around and reach this path and then move. Both of them do this. One is going to go to the virtual 0. One is going to go to the real 0. And there are ways to find out which one does what. I don't really care. I care about the shape of this. There's a lot of detail that you can get into with root locus, but the general shape, again, is what we're going to kind of stick to here. And so as it moves over, one of them goes to the virtual 0, one of them goes to the real 0. What I am interested in is finding this point where this happens. This is a breakaway, break in, break out kind of point. So we need to use our breakaway formula again. Okay, so the way we do that, let's write our formula again out here. Numerator times derivative of denominator minus derivative of numerator times denominator equals 0. And then, of course, for our formula, numerator is s, denominator is s minus 4 squared. That means the derivative of the numerator is 1, and the derivative of the denominator is actually 2s minus 8. Okay, and we could write this one out as well, and that would be s squared minus 8s plus 16 if we multiplied it out. Okay, so let's plug these back into our formula, and in doing that, we will get, let's see, that is an s, so we have s times 2s minus 8 minus the 1 times the denominator here, that is s minus 4 squared, set that equal to 0. Okay, and then let's multiply that out, and so we should end up with the, let's see, 2s squared minus 8s minus the s squared, don't forget the parentheses there, that would change the sign, be really careful. Okay, and subtracting these off, s squared, these cancel out, and then we have minus 16 equals 0. Alright, then that should give me s equals plus or minus 4. Okay, does this make sense with our locus, these breakaway points? There are 2. Or breakaway or break in, break out. So actually, this positive 4, at least, that is the point where our 2 poles are colliding. So yes, that is absolutely the point. We kind of already knew that one. The one we needed was the one over here in the negative part of the real axis. And it turns out that that must be the negative 4. So negative 4 is the point where we break into the real axis again. Okay, this is now our completed locus. Now again, there are different formulas you could use to see how far up this goes, see this radius, all of that. I don't care about that really. I just want to get down the basic shape of these locuses, or loci, I guess that is right. Okay, let's do another example. Okay, so for example 5, let's use a GOL of s equal to k 1 over s minus 4, just a part of our previous problem. We'll just borrow that denominator and see what happens there. Okay, so just filling in what we know about the problem, n equals 2, m equals 0, that means that q is also equal to 2 because that's the subtraction of these two. Our poles are at positive 4 again. That part didn't change. We don't have any zeros because we have a 1 up here. Let's fill in what we know. The real axis and the imaginary axis. Okay, so back here at 4, we have our double pole, and then we really don't have anything else. So as we come along here and we use that real axis rule, try and fill in any kind of migration path. Well, we don't really have anything to fill in here. But we know that these two poles have to migrate towards something, and Q is 2. So I know that I have 2 virtual zeros somewhere. Now, using the collision rule, they deflect off of the real axis. So they're going to go towards plus and minus infinity up here. Okay. And actually, that is about as much as we can tell. So the 2 poles just deflect off and they reach the virtual zeros that are out here. Okay, and that is going to be our completed locus. Now, there is one part of this that you can go ahead and take this a step further if you wanted to find the angle of the asymptotes. These may deflect off at plus minus 90 degrees, but then they might have a curvature towards some other point, and you can find that angle and determine that curvature as well. But again, I'm just interested in the basic behavior here. Okay, let's do example 6. Okay, well, let's use a GOL of S equal to K times 1 over S squared plus 4. Okay, so we'll just change it a little bit. All right, so what do we know about this problem? Well, we know the number of poles is still 2. If we look at that, we know that we have no zeros. So therefore, Q is equal to, the difference between these two is equal to 2. That's the virtual zeros. Okay, so let's go ahead and fill out our locus with as much information as we have so far. Okay, where are the poles? Well, the poles should be, let's go ahead and take that denominator, set it equal to 0. So S squared equals -4, and in order to solve that, you get a complex number, so S equals plus or minus J2. Okay, so actually we have 2 poles that are sitting on the imaginary axis. Okay, make that really obvious right there. 2 and a -2. We don't have anything on the real axis. We don't have any zeros, and we don't have any other poles. So we really can't use the real axis rule for this problem because there is nothing on it. So we do know that we have 2 virtual zeros. We have no real poles. So the only direction that we can move is along the imaginary axis, since there's no migration path on the real axis. So what's going to happen? Virtual zeros give us a clue, and then the fact that we can't move on the real axis gives us the other clue. These 2 poles will reach towards plus and minus infinity, and they will move on the imaginary axis. Okay, and again, these may lean towards a certain angle, and you could find that angle out if you wanted to, but this is the basic behavior. Okay, so we'll call this our completed locus. Okay, let's do another example. Okay, so let's do something a little more complicated for this one. We'll have a GOL of S, that is a K times S squared plus 2S plus 2. So we have a total of 2 zeros. And on the bottom, let's have a free S, and then an S4 plus 9S cubed plus 33S squared plus 51S plus 26. Okay, so here we have 5 poles. So N equals 5 and M equals 2 for our zeros. Okay, so we can calculate Q. Q equals 3. It's the difference between these two numbers. zeros subtracted from the poles. Okay, so we now have 3 virtual zeros. Okay. All right, so if you were to solve this, and you would have to use a computer program to solve this bottom one at least, you would find that the poles occur at 0, -3 plus or minus j2, -2, and -1. And that the zeros, which you can use the quadratic formula for that, occur at -1 plus or minus j. Okay. All right, so let's go ahead and start our locus. I'm going to put it down here this time. The imaginary axis and the real axis. Okay, and let's plot what we know about this problem so far. So starting with, let's say, the zeros. Let's start with the zeros. Okay, so they are at -1 on the real axis and then plus or minus j. So we have one here, and then we have another one here. Okay. And for the poles, we have 1 at 0, so 1 right here. Then we have another one at -2 and another one at -1. So I have one right here at -1 and another one at -2. And then our last set is a complex pair that happens at -3 and then plus or minus j2. Okay, so I think we've got all of those. All right, so you can see that we have some poles here on the real axis. We can use the real axis rule. So as we go across, and you may wonder, well, if I go across here, do I count these zeros since they're complex? They're not on the real axis. Do I count them? It really doesn't matter if you do or don't. Remember, they come in pairs, so it's not going to change the evenness or oddness of whatever number you already have. So moving our pen across here, we have a 1, fill in that path, and I have a 2 or a 4, and move across here, and I'm going to not count these. So I have a 2, and then I have 3, and I fill that in until -infinity out here. -infinity. Okay, so we've got that. So we used rule number 3. We have nothing that collides. So let's look and see what else have we used so far. We've used the breakaway, break-in, break-out kind of formula. It looks like we might need to use that here. So let's go ahead and assemble that. Okay. So just to save you some time, if you walk through this, for the breakaway formula will turn out to be, I'll write it out here, 33s to the 6th power plus 26s to the 5th power plus 97s to the 4th plus 204s to the 3rd plus 274 s squared plus 204 times s plus 52, and set that equal to 0. Now if you solve that, you will get roots at -2.7 plus or minus j times 1.1, -0.65 plus or minus j 1.6, and so that's 4 roots so far, and we have 2 more to go. We'll have a -1.4 and a -0.46. Okay, so if you evaluate all of these, it'll turn out that this value right here, and we can see that on the graph, this value is the only one that is actually in a migratory path. So it occurs right around here, And this is the point where these two roots, these two poles, will deflect out of the migratory path. They collide. So we use rule 4 for that. And they'll actually veer off and reach these real zeros. So one goes up, one goes down towards these two zeros. Okay? Now, you see that we have a pole here. This one's actually moving towards this virtual zero. It looks like 8 negative infinities, what I meant to draw. So it's actually doing that. It's moving over here. And so this one's actually fine. I don't expect any of these poles to come down to this axis. There's no zero for them to reach. But remember, our Q is actually 3. Here's one virtual zero. That means that we have 2 others. Virtual zeros will kind of split the whole circle. So we have 360 degrees. We have 180. So we'll have one over here and one over here. So I expect them to kind of have that look. That's not important. Just the general basic shape is for our class. All right, so they're going to reach this virtual zero up here and this virtual zero up here. Up here at infinity, towards the imaginary axis infinity, and towards the negative infinity of the imaginary axis as well. So this is now our completed locus for this more complex problem. Okay, so let's do 2 more problems. Okay, and actually, if you wanted to find those angles of those asymptotes, if we just step back real quick, back to example 7, we could do that. And it turns out, I think I said this before. I don't think I said the number, but it turned out to be about 60 degrees and minus 60 degrees off of the real axis that they would. So if I were to draw this a little more exactly, this migratory path would lean more towards a 60 degrees. And you could use your angle of the asymptotes formula that we discussed before to find that. Okay, so example number 8. Okay, so let's have a GOL for this one equal to k s plus 3 over s plus 1, s plus 2, and s plus 4. Okay, so let's fill in what we know about this problem. The zeros, we have one of them, so m equals 1, and 0 is at negative 3. All right, for poles, we have 4 of them, and the poles are at 0, negative 1, negative 2, and negative 4. Okay, we can start filling in our locus, so let's do that. I have a 0 here at negative 3. I have a pole at 0. I have a pole at negative 1. I have a pole at negative 2. And then I also have a pole at negative 4. This really goes in order. Okay, and label the axis. Okay, so everything is on the real axis. Let's use that real axis rule again. Okay, so at this point, up to this point, I have an odd number looking rightward. And then it's even until I get here, and then it is odd again. And even until I get here. And we just fill that in right there. Okay. So it looks like we've got a migration path, no migration path, and then no migration path, and then a migration path. Now, we didn't put our number of virtual zeros out here. Remember, that's n minus m. So 4 minus 1 is 3. So we should have 3 virtual zeros for this problem. And from earlier problems that we worked, it looks like these two poles are going to deflect off. We can use the collision rule for that. They should deflect off at plus and minus 90-degree angles and move towards virtual zeros. Okay, this pole should be moving towards this 0. And then we have the negative infinity, that virtual 0 out here. Okay, so once we fill in all of those directionals, we have our completed locus. The only thing that we might be interested in finding from this is this point right here. And I didn't mean to make a circle there. It now looks like a 0. Oh well. So what is that breakaway point? Well, we can find that. So the breakaway point, again, our formula out here is just like this right here. Okay, so if we find n equals to s plus 3, d is equal to all of that right there. I'll just write it out. We actually don't have to solve this, but we'll write it out. Okay, and then the n derivative is equal to 1, and the d derivative, we probably should multiply that out first. So we would get, real quick, multiplying that out. Okay, hopefully I didn't make a mistake doing that. And then finally we take care of that s that is there on the front. And there's a cubed term and 12s squared. Now let's combine these terms. Okay, and we have 2 cubed terms. We combine them to be a 7s cubed. And then 2 squared terms, we combine that to be a 14s squared. And then we have the 8s. Okay, so then that from this we can find the derivative here, and that would be 4s to the third power plus 21s squared plus 28s plus 8. Okay, and then I'm just going to write out the formula. I'm not actually going to solve it here. But if we plug these in, we would have s plus 3 times our derivative that we just found, 21s squared plus 28s plus 8, minus our derivative time is 1, and then our d factor right there, let's use that form. And that is s4 plus 7 s cubed plus 14s squared plus 8s. Now again, hopefully I did not make a math error doing that real quick. But if we solve this for s, then we should get, it looks like we would get 4 different points. And so one of those points should be on our migration path here along the real axis. And then that would be the one that we would choose. We'd need to evaluate that, the set of points that we find against the locus, and find which one makes sense. Okay, so I have one final example that we'll work through. This one is also a pretty simple example. We'll say that this is example number 9. Okay, all right, so let's use a GOL of s that is equal to k s plus 1 over s cubed plus 4s squared plus 6s plus 4. Okay, so we've got a third order equation on the bottom. All right, so for this problem, n equals 3, we have 3 poles. It turns out that the poles occur at -2 and -1 plus or minus j. We have 1, 0, and the 0 is at -1. Okay, so if we calculate our q, our number of virtual zeros, we get a 2, so we know we have 2 virtual zeros. All right, so I actually already did the breakaway formula. Well, we find out that our breakaway solution points or possibilities are -1.6 plus or minus j 0.65 and -0.34. Okay, so let's go ahead and start our locus. Okay, real axis and imaginary axis here. Fill in what we know. Our poles are at -2 and -1 plus or minus j. Okay, so there we are. And so we have 1, 0 at -1. That is right there. We can use our real axis rule because we do have poles or zeros on the real axis. Okay, and it turns out if we just move our pen across here, look rightward, and then we have a 1 odd, or we have 1, so it's an odd number. We can fill in that path until we get to this pole at -2. And then we know we can go ahead and fill in that directional, that our pole will migrate towards that 0. So it moves in this direction on that migration path. Okay, we have 2 virtual zeros to take care of, so it makes sense that these 2 poles would move towards virtual zeros at plus and minus infinity around the imaginary axis. Okay, and then for our breakaway points, at what point does this make sense? Okay, so -1.6. The -1.6 is it's around here. So plus or minus j 6.5. Well, does that make sense? Is it breaking out of the real axis at a complex value? No, we can throw out this pair actually, because that doesn't make sense. We would need a real value to break out of the real axis. So the -0.34, that's over here. That's not even in our path. So that one doesn't make sense either. There really is no breakaway point. And this is an example of, you can go ahead and calculate it. Doesn't mean that it has to happen. But this is our completed locus. Okay, so I hope that these examples kind of highlighted how to use some of the rules, the ones we use most often, how to use some of these formulas like the breakaway formula.